In this lecture, I'm going to cover difference amplifier and expand the structure of the difference amplifier to make it into an instrumentation amplifier, which is a really accurate and with a high differential gain. Just very good for building all these really accurate instrumentations. So let's take a look at the difference amplifier first. So it looks like this. You have two inputs, VI1 and VI2, and this is R1, R2, R3, R4, and here's VO. And we assume that R2 over R1 equals to R4 over R3, and also R2 equals to R4, R1 equals to R3. So literally, we just want to make R2 and R4 are the same, R1 and R3 are the same. So it's a symmetric topology. So there are two different voltage gains to evaluate the performance of the amplifier. The first one is called the differential gain. So that's a gain we are trying to evaluate or trying to derive first. Let's take a look at that one first. So since there are two different voltages are contributing to VO, so we can definitely use a superposition method to apply one voltage at once and then superimpose them together afterwards to get the overall VO. So for example, if we have VI1 only, then we are going to ground this voltage. You have to ground it. So you have R1, R2, VO. Then what's the voltage of VO? Because 0 volts, 0 volts, 0, so there's nothing here. So you can directly ground since there's no current flowing through this circuit. So it's overall 0 volts. It's not contributing anything. And we can get VO1 equals to what? Equals to VI 1 times minus R2 over R1. According to the inverting amplifier's topology, that's what we can get, right? So for the second case, VI2 only, then what's going to happen? So we have to ground VI1. And here's R1, R2, VO. So VI2 is working here. So it's a non-inverting topology because the input is being connected to somewhere around the non-inverting terminal. So in this case, we're going to get another VO. We call it VO2. So VO2 will be the voltage here because it's a negative feedback. So virtually, this voltage equals to this voltage. If you know the non-inverting terminal's voltage input, we just directly use non-inverting topology's voltage gain we derived in the past lecture and directly get VO1. So the voltage here is the voltage divider, so we can get VI2 times R4 over R3 plus R4, and which is the input of the non-inverting amplifier's voltage, and this will be then times the gain, right? So the gain will be 1 plus R2 over R1. So that's the overall voltage for VO1. But however, since we have this assumption already, So we can convert it into something else, which is simpler. R4 is actually R2. R3 plus R4 is same as R1 plus R2 times this guy, which is R1 plus R2 over R1. So you can directly cancel these two and eventually get VI2 times R2 over R1. So overall, VO equals to VO1 plus VO2, which is V, just add these two together, will be VI2 minus VI1 times R2 over R1, which is a gain here. And you can see that the reason we call this amplifier a difference amplifier, because it's amplifying the difference between these two terminals, is actually the non-inverting terminal's input minus the inverting terminal's input and times the voltage ratio from here to here or here to here. Doesn't matter because they are the same voltage, same resistors. Okay, so here is the voltage gain for the difference amplifier. Keep in mind. That's a difference input. And there's another type of input. It's called common mode signal. This is differential mode signal. Because the signals are being injected into the amplifier using two different terminals. So it's called differential mode signal. But common mode signal will be a totally different story. And this can be confusing. You must be wondering, so what is the common mode signal? Why do we need to evaluate this common mode signal over here for the amplifier? It's still the same circuit. It's just a different signal. All right, so why we have a common mode signal? So keep in mind that whenever you plug in something to the outlet on the wall, the AC signal is normally 115 volts and 60 hertz in the US. So this one will pass all these parasitic capacitors in the circuit, like the cables, and will not be removed 100% whenever it arrives here. So there will be some 60 hertz noise getting to the two terminals at the same time. And they are being treated as a common mode signal because they are arriving the terminal at the same time. So it's the same voltage, same phase, same amplitude getting into the two terminals at the same time. So we hope VCM is being suppressed instead of being amplified. So after we derive the gain for VCM, we hope the gain to be zero. So the performance of the amplifier will be better because the noise is not being amplified, but the signal, which is two voltages, are being amplified. So that's the purpose. So now let's take a look at the common mode gain of this difference amplifier. See what's the voltage gain for the common mode signal over here. If you look at this circuit, we still have this current flowing in that way to the output. So we can definitely list a equation over here. So this terminal is a VM. This is VP. And we are having VCM minus VM over R1 equals to VM minus VO over R2. And another thing is VM equals to VP ideally. And VP is a voltage divider, right? So VP is VCM times R4 over R3 plus R4. And VP equals to VM. So for these three equations, we should be able to find out the voltage gain for of a VO over VCM, which is a common mode signal input, right? Because this is a symmetric structure, so we assume that R2 equals to R4 and R1 equals to R3. Again, so now let's derive it. So before we move forward, let's take a look at this. How can we reduce the number of variables in this equation? So we don't need VM. We just need the relationship between VO and VCM, right? So VM should be substituted. And we can see that VP equals to VM, so this is actually VM. So we can use this part, substitute VM here and here, and then to find out the VO and VM, what kind of equation can be used to describe the relationship between VO and VCM. So that can be a doable strategy. So now let's substitute VM over here. So this is VM, and we're going to use this as VM in this equation. So we are having VCM minus this entire thing, VCM times R4 over R3 plus R4, and over R1 equals to VCM times R4 over R3 plus R4 minus VO and over R2. All right. Then what's next? We can times R2 on both sides of the equation and move R1 to the other side. So we're getting VCM times R2 over R1 minus VM times R4 over R3 plus R4 times R2 over R1 equals to VCM times R4 over R3 plus R4. Am I making this right? This should be VCM, not VM, I think. Yeah. Yeah, VCM. This one minus VO, okay? So let's separate anything contains VCM from VO, right? So here, VCM times R2 over R1 minus R4 over R3 plus R4 times R2 over R1 minus this guy, R4 over R3 plus R4 equals to minus VO. Okay? This one minus this, minus this. Okay, and given that R3 equals to R1, R2 equals to R4, so this one is equivalent to this. R2 over R1 plus R2 times R2 over R1 minus R2 over R1 plus R2 equals to minus VO. And then we know that, let's move this one to the other side, so we only have this part on the left. So we are getting R1 plus R2, and then what? This need to be R2 times R1 plus R2 minus R2 squared minus R1 times R2 equals to minus VO over VCM. All right. Now, you have R1 times R2 here, R1 times R2 here, so it's being canceled. And R2 squared here, canceled as well. So eventually, whatever you have a minus sign or not, VO over VCM is going to be 0, ideally. So if you have this very symmetric circuit topology, the common mode gain will be something close to 0. Okay, which is what we need. We don't want to amplify the noise. All right, so there's another concept that just comes out from this conclusion. It's called CMRR, which is common mode rejection ratio. Which is the differential gain AD over ACM and percentage. Okay, and you hope this one to be as large as possible, which means you need this guy close to 0. You need this guy to be as large as possible to evaluate the performance of the op-amp you can buy off the shelf from the market. Okay, now we know that the difference amplifier is a really good topology because it is able to amplify the difference between these terminals and reject the noise over here. So we want to use it because it looks great. In that case, let's use it in the circuit, but try to improve it slightly. So there's a concern over here. So if the two inputs are being directly connected to the two, the circuit is being directly connected to the two inputs, you have a resistor here being directly associated with whatever in the previously over here in the previous stage. So in that case, the voltage can be degraded or being affected by this voltage divider effect over here. So you can use something to isolate it. In that case, we are getting something very interesting, and the structure is called instrumentation amplifier. Okay, let's look at it. Here's the original difference amplifier. No problem. So the purpose here is to isolate the input from the output. Remember, we just learned one thing in the previous lecture, which is a buffer can do this job for us. But keep in mind, always negative feedback. So the feedback need to go to the inverting topology, the inverting terminal over here. Same thing, inverting terminal should be fed back to the circuit. So now I have VI1, this is still the same input, but now they are being isolated from the output. All right, that's why you need two buffers at the front stage for the instrumentation amplifier. But still not good enough, because the amplification here is, if we call this VO1, this is VO2, and we know that the amplification will be VO2 minus VO1 times R2 over R1 as a differential gain for VL. So can we increase the gain? Since we already have a buffer, why not add some resistors to the buffers to just add more gains to the amplifier, to the overall amplifier? So that's why we came up with a slightly different topology with the same concept, but we just added two more resistors in there. So let's look at it over here. That's a difference amplifier, still pretty much the same concept. All right. And negative feedback, don't forget about that. And two inputs. And we name this as 2R1. Doesn't matter. It's just the value. Okay, it's just easier for calculation. So these are two equivalent resistors. We name it R2, R3. They are symmetric structure, and R4, R4. And this is grounded. This is VO. And there are two intermediate VL. This is VO1. This is VO2. So here's the question. What's the voltage gain for this guy? Because we know this is a difference amplifier for here, for this part. So we know the common mode rejection ratio should be really high, and the common mode voltage gain should be 0, since we just derived it in the last few pages. So now, after we added this front stage over here, what's the differential voltage gain? That's the question. So we're going to do it now. So look at the structure. So since we know that the input resistance for all the op-amps are huge, right? So no current is gonna get inside all these op-amps. So the current can only flow through here and to here. Nothing can go inside the op-amp. So it's gonna go that direction and go to the output. So that's the direction of the current. And now it's the same current everywhere. And we know that they are, negative feedback for these two op-amps. So VI2 here, VI1 here, no problem. So we got all these voltage nodes, and we know the current. We just assume it as I, and they should be all equal to each other. So let's just derive it using Ohm's law for this purpose. So first of all, we don't need to care about this part because we already know the voltage gain for this part. We just need to find out the relationship between the intermediate VL and the VN1, VN2. Okay, that's it. So first of all, VO2 minus VI2 over R2 should be the same current as VI2 minus VI1 over 2R1. It's the same current. And then VI2 minus VI1, this guy, over 2R1 is the same current over here. So we need to use VI1 minus VO1 over R2, which is this minus this over R2, same current. So these two equations. And this should be enough to give us the result. Okay? So from this one, we know VO2 is what? VO2 is R2 over 2R1. Just move this to here. And times VI2 minus VI1 plus VI2. And from here, we know VO1 equals to what? VO1 equals to VI1 minus R2 over 2R1. And then VI, what is this? Oh, VI2, I guess. Yeah, VI2 times VI2 minus VI1. All right, so these are these two voltages. And because we are just interested in the difference between these two voltages, because they are being used as two inputs for the difference amplifier as well. We don't want to know what are they exactly, we just need to know the difference. So we are interested in VO2 minus VO1, which is this minus this. So this part will be cancelled. No, they are not being cancelled. They will be duplicated. So because this minus this will be, we'll change the sign here to be a plus. So you are getting R2 over R1, VI2 minus VI1. And then here, plus VI2 minus VI1, which is VI2 minus VI1 times 1 plus R2 over R1. All right, so that will be VO2 minus VO1 being used for the difference amplifier. So after that, since we know the difference amplifiers gain is this minus this times the ratio here, right? So let's do it. So VO equals to VO2 minus VO1 times R4 over R3. And we know this from here, which is VI2 minus VI1. So we can now bridge these two results together to find out the overall voltage gain. So now we are able to bridge VI1, VI2 with VO. So that will be the overall result as a differential gain for the instrumentation amplifier. And this is what we need for this calculation. All right. Okay, so this is everything I'm going to cover for this lecture. I'm going to see you in the next video.